Hello, am I audible? Okay, I hope am I audible? So I am Subrata Samanta from IIT Kanpur. So so I am one of the TA for the thermal physics course that is taken by Professor Demal Banerjee in this semester. So today I will solve assignment six problem, right? And okay, so let me share my screen first. Yeah, I hope my screen is visible now, right? So yeah, so this is assignment six problems, previous year assignment problems, so that I will solve. So hope at the end you will able to solve this week assignment problems. So very similar problems. So okay, so before that, so if you have any questions, you can ask from the previous week or any doubts. Okay, don't hesitate to ask any questions. Okay. You can also write up in the chat box, okay, if you want. Okay, so if not, then I will start the problems. Okay, one by one. So in the first problems, this is the problem number one. Okay. Yeah, so in the first problem is that they calculate the van der Waals constant for hydrogen given that Tc 33.2 Kelvin and Pc 12.8 atm atmosphere and R is 0.082 liter. So the Tc given, Pc given, and the values of R is given, right, in the problem. Okay. We have to calculate the van der Waals constants for hydrogen. Okay. So what are the van der Waals constants? Now van der Waals constants are A and B, right? So you have to calculate. So if you so okay, so go to the new page. So in the first problems, calculate the van der Waals constant. So if you look into the van der Waals equation of state, so the equation of state, van der Waals equations of state. Okay, for 1 mole of gas. Okay, right. So P equals to, this is the pressure, equals to RT over V minus B minus A over V square, right? So where A and B are the van der Waals constant, right? So where A and B the van der Waals constant. Okay. So where A and B are the van der Waals constant. So in this problem, you have to determine the values of A and B. So in the first problems, okay, so you have to determine the values of A and B. Okay. So how to determine the given that Tc and Pc, okay, and also the values of R is given, the universal gas constant. Okay. So how to calculate Tc, Pc and Vc? So you calculate the Tc and Pc. So at critical point, so critical point, that means Tc, Pc and Vc, the critical points. So del P over del V, right, at fixed temperatures at critical point, that is Tc, Pc and Vc, equals to 0, which is equals to del 2P del V2, right, at temperature T, Tc, Pc, Vc, right. So at this temperature Tc, Pc, Vc both are derivatives. Okay, so the del P del V at a fixed temperatures, and del 2 P, del V2 both are 0. Okay, so there is no maximum and minima in the PV plane. Okay, so once you do this, it is very straightforward to calculate. Okay, so the for van der Waals gas, okay, so the values of A, okay, the expressions of PC, yes, so PC is basically your A over 27 B square, and VC is 3B, and TC is 8A over 27 RB, right? So this is a critical pressure. So this PC, critical pressure, this VC is critical volume, and this TC is critical temperature, right? Okay. So in the problem, the PC and TC value is given. So TC is 33.2 Kelvin and PC 12.8 atm. So given TC is basically the values of TC is 30. Sorry, the values of TC is 33.2, right? Let me check. Yes. So 33.2 Kelvin, and values of PC is given 12.8 atm, right? So now, so in the PC both A and B are there, right? In the TC also both A and B are there, right? So once you divide PC over TC, or let's say TC, sorry, once you divide TC over PC, this becomes, so TC is 8A over 27 RB, and then PC, so if we multiply it with 1 over PC, that 27 B square over A, right? So then the numerator and denominator A cancel, okay, and 1 of B cancel, right? So we are left with 27 also cancel, so we are left with B over R, and there is a 8, so 8B over R, right? So now you just plug these values, okay, TC and PC, you can calculate easily B, because R is also given, so the values of R is 8.314, right? So 8.314, and the unit, yes, unit is basically liter mole, sorry. So the unit are in which units is given, yeah, so the liter atmosphere per mole Kelvin, and this is atmosphere, okay, fine, good. So liter atmosphere per mole Kelvin, okay. So then we can easily calculate the values of B is 8.314. So I have to convert this, okay, because liter atmosphere, sorry, this one is joule, so liter atmosphere is 0.082, right? Let me check. Yes, so 0.082 liter atmosphere per mole Kelvin, sorry, so 8.31 per joule per mole per Kelvin, okay. So if you convert this unit, so 0.082, right? So therefore the values of B is 0.082 times your values of TC, so given is 33.2, and in the denominator the values of PC, so what is the values of PC? 12.8 atm and then 8, right? So once you calculate this, okay, we get that 0.0266, right, liter per mole. So this is the values of B, right? So once you calculate the values of B, so this is one thing we calculated, okay, and next we have to calculate the values of A, okay. So how to calculate the values of A? From this, because you know that yeah, so PC, let's say PC on is good. So PC actually a over 27 b square. So use these relations because PC is given. So use the relations to calculate a. So PC is a over 27 b square. So therefore a equals to 27 b square times PC, right? So I already calculated the values of b, so just plug these values. So 27 0.0266 square, okay, and then PC. So PC value is 12.8 atm. So at the end the values basically so the unit is yeah, so atm. So this is b square, so liter square over mole square, right? So once you calculate this, so this is basically now have to check that the expressions is sorry the answer is given in bar. Okay, so you look into this, all the answer is given in bar, and this one is Newton meter square per mole square. So this is also units of A, right? Because if you just look into this, so bar are basically so 1 Pascal, right? So 1 bar, okay, so 1 atm equals to 1.013 bar, right? 013 bar, and liter is basically your meter cube, right? So atm, and atm is Newton per meter square. So therefore this is also unit the Newton per meter square. So what is the unit the dimensions of A is basically the pressure times the volume, right? So Newton per meter square pressure, and the volume is meter cube, right? Okay, and then divided by, so this is basically n square, so divided by mole square. So this is basically divided by mole square, okay. So which is equals to Newton, yes, so Newton per yes, so Newton meter per mole square, Newton meter to the power 4, because V is L cube. So yes, so this is m to the power 6, because your V is basically area, so L cube. Okay, so this is basically a Newton per meter square and m to the power 6, so Newton meter to the power 4. Okay, because here volume is basically your dimensions of m to the power 6 L square, right? So this is the thing. Sorry, n square a over v square, that is basically your pressure, okay. So n square a over v square, so pressure, and this is v square, right? And v is m cube, so that's why m to the power 6, okay, and that's correct. So this also unit is correct, okay. So Newton meter to the power 4 per mole square is also correct, right? So then, but we have to calculate in bar, okay. So because we have expressed in terms of liter per mole square, so we use bar, so that's why we multiplied with this number, okay, multiplied with this number because this is in the atm, so I convert this, so 1 atm equals to 1.013 bar, okay. So this is basically 27.0.0266 times 12.8 times 1.013, this is basically bar liter square over mole square, right? So this is important. Okay, if you convert to liter to atm to bar. Okay, so if you convert atm to bar, okay, so sorry, if you have not any questions, so please mute yourself. Hello, if you do not have any question, please mute yourself. Okay, so if you multiply with this number to 1.013, okay, so if you multiply with this number 1.013, right? So once you multiply with this, we get that 0.247 bar liter square over mole square, right? So this is your result. Okay, so let's check the answers. Okay, this is in the answer or not. So yes, so the first one, right? So values of A 0.247 in the unit bar, and the values of B in the unit liter per mole. Okay, so bar liter square per mole square in the unit of A, and the B is liter per mole. Okay, so the answer A is correct, right? So this number is important. Okay, so 1.013. Okay, you have to multiply with this. Okay, so that is the one of the crucial point in this problem. Okay, so we calculate the values of B, this one, and using these values of B we can calculate the values of A. Okay, so now in the next problem, so what is the next problems? Okay, so far any question? Okay, so if not, then I will move to the next one. So in the next question, calculate the boil temperature of 1 mole of helium gas, right? Basically the helium gas we can consider as a van der Waals constant, van der Waals gas. Okay, where the van der Waals constant are A, this value, okay, and the values of B is given, okay, and the values of R is also given, okay, and calculate the boil temperature. Okay, so first we want to know that what is the boil temperatures. Okay, so if you know the virial expansion, right? So the virial expansion basically, so the PV over RT we can write as a series of 1 plus B over V plus C over V square plus dot dot dot. Okay, so this B is temperature dependent, is a function of temperature. C also is a function of temperature. Okay, so this B is the second virial coefficient. Okay, so this B is the second virial coefficient. Now at temperatures, okay, at temperature let's say TB, where the B of TB equals to 0, then so this temperature TB is called the boil temperature, right? So this TB is the boil temperature where the second virial coefficient is 0. Okay, so now in the given problem, so if you look into the problem where the van der Waals equation substrate, right? Van der Waals gas, so helium gas, so they are using helium gas. Okay, so helium gas is a real gas. Okay, and we can consider as a van der Waals gas. Okay, so they follow the van der Waals equation substate. So in the van der Waals equation substate, so P equals to RT over V minus B for 1 mole gas, right? So for 1 mole van der Waals gas, this, so we can write this RT and 1 minus, so RT over V and 1 minus B by V inverse B over V and minus A over V square, right? So this is basically RT over V 1 plus B over V minus B square over V square plus dot dot dot. Okay, I think there is some 8. 1, no, I mean this is 2. Okay, so minus B square over V square and minus A over V square. So now if we just RT over V plus RTB over V square minus A over V square minus no, this is a plus, so plus B square over times RT over V cube, okay, plus dot dot dot, right? So now if we just compare, this is the coefficient of, so if we take this, that PV over RT equals to 1 plus RTB minus A, right, over RT. So we take this RT, so this is basically B minus A over RT times 1 over V plus B square times V square plus dot dot dot, right? So now we compare these equations to the virial expansion, these equations, right? So let's compare that the BT, basically the coefficient of 1 over V is B minus A over RT, right? The coefficient of 1 over V. So this is your BT. Okay, the second virial coefficient is B minus A over RT. Okay, so now at temperature TB, at boil temperature TB, so at boil temperature TB, your B minus A over RTB equals to 0. So therefore the boil temperature TB is B R over A, right, or A over RB, sorry, the boil temperature opposites, A over RB, right. Now in the problem the values of A is given. So what is the values of A? Yes, so this one 3.59. So your boil temperature TB is A over RB. So plug these values, 3.59 times 10 to the power minus 3 over R value 8.31 times 2.41 times 10 to the power minus 5, right? So the denominator. So now if you check the unit, so this one is the Newton meter square per mole square, this one is the meter cube per mole, and this one joule per mole per Kelvin. Okay, so then this TB, the unit is Kelvin. Okay, so all are in the SI units. Okay, so there is no problem. So you just calculate this, you get that this is 17.9257 Kelvin. Okay, so now check the answers. So 17.9, yeah, so the closest answer is 17.93, right? So you have to choose the closest answer, okay, because the 9257 is approximately 17.93 Kelvin. Okay, okay, so you have to choose the closest answer, okay, closest option. Okay, so the option B is correct. So in this case option A is correct. Okay, so far any question? Okay, so if not, then I will move to the next one. So the second virial coefficient of a gas is given. Calculate the volume of 1 mole of the gas at 27 degrees centigrade and 5 atm pressure, right? So in this case the second virial coefficient is given. Okay, so in the previous problem, in the problem number 2, we calculate the boil temperatures. Basically we need the second virial coefficient, right? But in the third problem the second virial coefficient is given. That means this Bt is given is 0.02 liter per mole. Okay, the values of the second virial coefficient. So if you look into this, yes, so this is the second virial coefficient. So you have to calculate the volume and given, so in this problem you have to calculate the volume of 1 mole of gas at 27 degrees centigrade and 5 atm pressure. Okay, so in the problem number 3, the pressure is given 5 atm, temperature is given 27, so 300 Kelvin, right? And your number of mole n, okay, so n equals to 1 mole of gas. Okay, right? So since this one, so in this problem the second virial coefficient is given, so I have to truncate this virial expansion. So this series, okay, or this series, okay, up to this point. Okay, so I have to truncate up to this point. Okay, so that means your equations of state PV over RT equals to 1 plus B over V, right? Where B is given 0. Yeah, so what is the values of B? 0.02. So I think 0.02, right? Yes, so 0.02 liter per mole. So this 0.02 liter per mole, that is given, right? And also V is given, sorry, P is given and T is given, and calculate volume. So I have to calculate V. R value also given. Okay, we know that 0.0, since all are in the liter. Okay, liter, this one is the atm, so you have to use R in the unit 0.082 liter atm per mole. Okay, yes, so R in the units, yeah, liter atm per mole per Kelvin. So liter atm per mole Kelvin. Okay, so in this unit you have to use. Okay, so depending on the content, okay, you have to, the problem you have to use that which values of R, 0.082 or R is 8.314 joule per mole per Kelvin. So if in the liter and atmosphere, okay, then you have to use this. If we use in the joule, then you have to use this value. Okay, so this is crucial. Okay, okay, so in this case, since sorry, so in this case all are in the liter, so I have to use this value. Okay, 0.082, right? So now, so since this, you have to, if you solve these equations, okay, so this equation is basically your P times V square, okay, minus RTV minus RTB equals to 0. Okay, so in the problem this is beta. Okay, so I use beta instead of B. Okay, so now this is a quadratic equation in V square V. Okay, this is a quadratic equation in V, so there is a 2 solutions, right? So the values of V is basically your, so this is nothing but your A x square, sorry, a v square plus bv plus c equals to 0. Now we know what is the solutions, is minus b plus minus b square minus 4ac, right, over 2a, right? So if we use this, so your b is, so in this problem your b is minus rt, okay, C is minus RT beta, A is P, right? So therefore so this is B and C, right? So therefore if we plug these values here, so your V is equals to RT, right, plus minus square root of B square, so R square T square. Now for AC, so A is positive, C is negative, so plus, right, because C is negative, 4 RT beta times P, okay, over 2P, okay. Up to this point clear, right? Okay, so then this is basically, now if we take RT, because both R square T square and RT, so we can take RT value. So if we take this RT, then 1 plus minus square root of 1 plus 4P beta over RT, right, then this is divided over 2P, right. So now you plug this value. So what is the values of R? It's 0.082 times, what is the values of T? T is 300 Kelvin, right? So use this R, so T 300 over 2 times P, right? So what is the values of pressure? Is 5 atm, right? So 5 times 1 plus minus, now I have to compute this one. So this one basically 1 plus, what is 4, P is 5 and beta is 0.02 over R value 0.082, right, and then T again 300, right. So after simplifying, you just use calculator, okay, to calculate this. So once you calculate this, so you get the 2.46, this value is 2.46 times 1 plus minus, right. So we calculate this value, so this one, this one, if you calculate this value, so this gives 1.078, right. So now you tell me that which sign I will choose, plus sign or minus sign, right, because this one is greater than 1, okay. So this number is greater than 1, right. You have to calculate the volume V. So volume cannot be negative, right. Volume basically your, that's area and volume, so volume cannot be negative, right. So then you have to choose plus sign, okay, not the minus, okay. So then the value V is 2.46, 1 plus 1.078. So this is basically 2.46 times 2.078, this is 5.11 liter, right, 5.11 liter. So this is the volume, okay. So let's check the answer, okay, if it is in the option or not, okay. So 5.11, yeah, so the option C, it is given, okay. So the option C is correct, okay. So far any question? So you have to always check. So now you can ask the question, okay, so some so it can have value less than 1, then which sign I choose, right? Because if you look into this, okay, So this is basically 1 plus some number. Okay, so it's 1 plus some number, so this is always greater than 1. Okay, so this value, okay, so that is I mark it with the red colors. Okay, so it's always greater than 1. Okay, so the values of this. Okay, so that means you have to always choose the plus sign, not the minus one. Okay, because this one is a 1 and this is always greater than 1, right? Since the volume cannot be negative, okay, so you have to always choose the plus sign. Okay, okay, fine. So hope it's clear now, and okay, so I will move to the next question. Yeah, so the question number 4. So in this question, a gaseous hydrocarbon obey a deterioracy equation, right? So this is not a van der Waals. Okay, so it's a deterioracy equation. Okay, another equations of state for a real gas. Its critical temperature, so its critical temperature is 33 degrees centigrade. Okay, and its critical volume is 0.142 liter per mole. Calculate its pressure of, calculate its pressure if 10 moles of gas occupy a volume at 27 degrees centigrade. Okay, so first note down what are the givens in the problem. Okay, so the critical temperature Tc is given 33 degrees centigrade. So first we convert it to Kelvin, right? So this is basically 306 Kelvin, right? And critical volume is also, critical volume is given Vc. So this C and Tc are the critical. Okay, critical temperature, critical volume. So Vc is 0.142 liter per mole, right? And yeah, so these two given, but the constant, the gas constants are not, gas constant, not the constant in the A and B. Okay, so these are not given. Okay, so you have to calculate from these two. Okay, so from Tc and Vc you have to calculate the values of A and B. Okay, they're known as the van der Waals constant, but since the equations of state is not the van der Waals. Okay, so the values of Tc Vc for this gas is not same as the van der Waals gas. Okay, so first note down this. Okay, so what are the TCPC value for deterioracy gas? Okay, so for deterioracy gas, okay, so what is the equations of state for deterioracy gas? Let's say for n mole. Okay, so the equation of state of for n mole. Okay, so P equals to n RT over V minus NB, right, times e to the power minus NA over RTV. Okay, so this whole in the exponential. Okay, so e to the power minus Na over RTV. So this is your equations of state for deterioracy gas. Okay, for A and B are the van der Waals constant. Okay, so and so again the same technique. So del P over del V at critical, at fixed temperature, at the point Tc, critical point Tc Pc Vc is equals to 0, which is equals to del 2P del V2 at critical at fixed temperatures, at critical temperature Tc Pc Vc, again 0. Okay, so both are 0. So this is the conditions to calculate Tc Pc Vc. Okay, so once you calculate for these equations of state, okay, so you get that Vc, the critical volume is 2B, not 3B. So for van der Waals gas you get 3b, okay, but for deuteracy gas it's 2b, and Tc is A over 4rb, okay, it's very simple, A over 4rb. So in the problem the Vc value is given, so your Vc is 0.142 liter per mole. From this we can calculate B. So what is the values of B then? It is divided by 2, right? So this is Vc over 2. So the values of B is basically 0.71, okay, liter per mole. And from the, so once you know the values of B, okay, we can use this and these equations, because Tc is also given. So the values of Tc is 306 Kelvin, okay, this is also given in the problem. So you can calculate the values of A. So it's 306 times 4rb, right? So the values of A then 306 times 4. What is the values of R? If we use same unit, liter, so the values of R 0.082 times the values of B 0.71. So the unit is 0.071. This is 0.071. And yeah, 0.071, right? So the unit is liter square atm per mole square, okay. So once you calculate this, right, so this is basically 7.126, right? So liter square atm over mole square. So this is the values of A, and this is the values of B. So once you know the values of A and B, okay, we can calculate the pressure. So how to calculate the pressure? So then the pressure is basically again, so for which mole? Yes, so for 10 mole of gas occupy volume 4.86 and temperature, okay. So n is given 10 and volume V is 4.86 liter and temperature is 300 Kelvin, right? So 27 degrees centigrade means 300 Kelvin. You have to calculate the pressure P, okay, and we know the values of A and B now, okay. So the next problem is that calculate the pressure, okay. So then the pressure P is basically safe to use these equations, right? So it's 10 times, because I wrote 1 time, so nRT over V minus NB e to the power minus Na over RTV, right? So plug this value, n is 10, R value 0.082, T is 300, okay, and your volume V is 4.86 minus 10 times the values of B 0.071, okay, so both are same unit, okay, since we subtract this, and then e to the power minus your n is 10 times what is the values of A, we just calculate this 7.126 over, this is whole in the exponential, okay, this is divided by R 0.082, temperature 300 and the volume 4.86, right? and this is your exponential, right? So e to the power minus this. Yeah, so once you calculate this, so this gives 32.66 atm, right? So check the unit, because this is in the atm, right? So the values of a in the atm, and yes, so RTV also in the v, r in r also I use the values of r in the atm, right? So 0.082 in atm. Okay, so yeah, so if you want to cross check this, yeah, this is r, right? So liter atm, so I have to use atm. Okay, fine. So then this is the atm. Okay, so 32.66. Okay, so let's check the option. Okay, if it is in the option or not. Okay, so 33 point, yeah, 32.66, so the option D. So option D is correct. Okay, okay, so far any question? You can also write in the chat box. Okay, so if not, then I will move to the next one. Okay, so in the next problem, so determine by using the reduced van der Waals equation how many times the gas temperature exceed its critical value. Okay, so this is basically the reduced van der Waals equation, right? So first you know that what is the reduced van der Waals equation. I wrote, and how many times the gas temperature exceed its critical value if the volume of the gas equals to half of the critical volume and pressure 12 times of the critical pressure. Okay, so first the reduced variable. Okay, so first is given that the volume of the gas, so V, is equals to half of the critical volume, so half times Vc. This is the critical volume Vc. Okay, and your volume V equals to half times Vc, and the pressure P 12 times critical pressure, so 12 times Pc, right? And you have to calculate T, the gas temperature exceeds critical value, so T over Tc, right? So you have to calculate the T over Tc, okay, the ratio of T over Tc, okay, where the ratio of V over Vc is given half, and the ratio of P over Pc is given 12. Okay, so in the problem you have to calculate the ratio of T over Tc. Okay, so the problem is clear, right? And you have to use the van der Waals equation, okay, or the reduced van der Waals equations. So the reduced van der Waals equations, nothing but we just rewrite in terms of some other variables. Okay, that's I will discuss now. Okay, so the problem is clear, right? So to calculate T over Tc using van der Waals equations. Okay, so we know that what is the van der Waals equation, right? So van der Waals equation is basically P equals to RT over V minus B for 1 mole of gas minus A over V square, let's say for 1 mole. So for 1 mole of gas, this. Okay. So if we write these equations, okay, in terms of let's say the reduced variable. So I define some reduced variables. It's basically, let's say PR. Okay, so reduced PR means the reduced variable, basically P over PC. Okay, and VR V over VC, and TR T over TC. Okay. And we know for these equations, okay, what is the values of PC, VC and TC, right? So where the PC, for these equations we know that what is the values of PC, right? So PC is basically 27, sorry, A over 27B square, okay, and VC is 3B, and TC, okay, is 8A over 27 RB, right? So now in the second step you have to define this variable, okay, and write these equations 1 in terms of PR, VR and TR. That is your reduced van der Waals equations. Okay, so once you do this, okay, so the reduced van der Waals equations, so reduced van der Waals equation is basically PR plus 3 over VR square, right, times VR minus 1 over 3 equals to 8 over 3 PR. Okay, so this equation, the equations 1 is now converted to this. Okay, is a reduced equation because in terms of reduced variable PR, VR and TR. Okay, so these are the reduced variables. Okay. So I'm doing nothing, but I'm just changing the variables. Okay, so P, V and T. So I'm changing the variable P, V, T to PC, PR, VR and TR. Okay, but the gas constants R is gone away. Okay, so only basically there's some just number. Okay, so 3, 1 over 3, 8 over 3 and the variables. Okay, PR, VR and TR, right? So this is basically reduced van der Waals equations, right? So now in the problem your PR value is given, right? It's basically 12, it's P over PC is 12, and VR is given, is V over VC is half. So you have to calculate TR, T over TC, right? So you have to use these equations. Okay, these equations, right? So plug these values PR, VR, okay, and you can calculate TR. So 12 plus 3 over 0.5 square, or basically 1 over 2 square, times 1 over 2 minus 1 over 3 equals to 8 over 3 times TR. Okay, so then this is basically 12 plus 12, right, times 6, 1 times 8 over 3 TR, right? So this implies that TR equals to 3 over 8 times 24 over 6, right? So 4 and 2, so 3 over 2, right? So it's basically 1.5. So then this implies that T equals to 1.5 times TC, right? Okay, So now go back to the problem. How many times the gas temperature exceed its critical value, right? So that means T, so we got the T are equals to 1.5 T. So 1.5 times, right? So then the option is 1.5 A. Okay, how many times? The option A is correct. Okay. Up to this point is clear? Okay, so far any question? Okay, so then I will move to the next one. So basically problem number 6. Okay. Yeah, so in this problem, so for a constant volume gas thermometer, the gas is to be filled at low temperature, low pressure, high temperature, low pressure, low temperature, high pressure, high temperature, high pressure. Okay, so there is nothing to do with just a statement. So for a constant volume gas thermometer, yeah. So in this case, this is basically an ideal gas, right? So the constant volume gas thermometer, the gas is nothing but the ideal gas, right? So they behaves like an ideal gas, right? So any real gas behaves like an ideal gas in what conditions? Okay, and which conditions, right? So the condition where the high temperature and low pressure. Okay, so at high temperature and low pressure, okay, a real gas okay, behaves like an ideal gas, behaves like an ideal gas, right? So therefore the gas to be filled at high temperature and low pressure. So option B is correct, right? Because the constant volume gas thermometer where the gas behaves like an ideal gas. Okay, so that means this must be at high temperature and low pressure. Okay. Okay, so yeah, so far any question or any doubts? Okay, so if not, then I will move to the next one. So the pressure of the problem number 7, the pressure of the gas in a constant volume gas thermometer is 80 centimeter. Okay, so here the 80 centimeter means that the pressure is basically the 80 centimeter of mercury. Okay, so you know that the standard pressure is 1 atmosphere is basically 76 centimeter of mercury, right? Hg. Okay, so here the 80 centimeter basically the so okay, so you may ask that the pressure why is the pressure in the centimeter, right? Because the pressure of the gas is a constant volume gas thermometer is 80 centimeter means that the 80 centimeter of mercury. Okay, while the 1 atm is basically 76 centimeter of mercury. Once you convert, we just divided by 80 over 76. Okay, that is basically gives you some atm. Okay, so that is equivalent to this. Okay, and 193 centimeter of mercury, okay, at ice point and at steam point, right? So ice point is basically 0 degree centigrade and steam point is the 100 degree centigrade, okay. So the ice point is 0 degree centigrade and steam point is a 100 degree centigrade, okay. When placed in a hot bath, okay, the pressure reached 100 centimeter of mercury again, okay. Find the temperature of the bath, okay. Okay, so first note down the data table that is given. So this is problem number 7, okay. So the problem number 7 is given that at ice point and at steam point, right? So at 0 degree centigrade your pressure is 80 centimeter of mercury, okay, and at steam point 100 degree centigrade, and next is the bath, okay, hot bath, okay. So at 0 degree centigrade is 80 centimeter of mercury and 100 degree centigrade, what is the pressure? 109.3 centimeter of mercury, right? And at bath, what is the pressure? You have to calculate, right? So pressure we have to calculate, but the temperature is given. Bath temperature is given. T is yeah. So 273 and 446. Yeah, 273. What is the bath temperature? Trying to change in the Kelvin. Yeah, so the bath temperature, sorry, the pressure is given 100 centimeter of mercury, and you have to calculate the temperature of bath. Sorry, so the reverse one, okay. So, the pressure is given 100 centimeter of mercury. So you have to calculate the temperature, okay. And 100 degree centigrade pressure is given, at 0 degree centigrade pressure is given, okay, but at which temperature the pressure is 100 centimeter of mercury, you have to calculate, right? So how to calculate this? Yeah, so we have used this formula, that is basically theta, okay, this is theta p, okay, at some pressure p, okay. So it's basically p theta minus p naught, or p 100 minus p naught times 100. So where p 100, this is basically p 100, this is p naught at 0 degree centigrade, p 100 basically p 100 at 100 degree centigrade pressure, and p theta, let's say 100 centimeter of mercury, okay, and this theta is the temperature I have to want to calculate. So this is basically theta, okay. So now if we plug these values, so 100 minus p naught is 80, okay. Yeah, so this is because this is, there is a ratio, right? So p theta minus p naught divided by p 100 over p naught, okay. So if we divided every, so let's say 100, I have to change in ATM, so 100 over 76, 80 over 76, or p 100, 109.3 over 76 minus 80 over 76, right? So is equivalently is basically 100 minus 80, 109.3 minus 80, right, times 100. Okay, so this is basically 20 over 29.3 times 100, right? Okay, so it gives you 62 point, sorry, 68.26 degrees centigrade, okay. Okay, so this point is clear or not? So this is basically 100 degrees centigrade. Okay. So this is basically 100 degrees centigrade. That's why it's a degree centigrade. Okay, because otherwise it's the basically ratio, so it's cancelled, dimensionless number. So this one is a dimensionless number. Okay, and this is basically 100 degrees centigrade. So at the end, so you get in the degree centigrade. Okay, so then the values of theta is 68.26 degrees centigrade. Okay, so let's check the answers. Okay, so 68.26. Yeah, so the problem number, yeah, so the option D. Okay, so the option D is correct. Okay, so far any question? Okay, so if not, then I will move to the next one. Okay, so how many questions are left? Yeah, so 3. So the problem number 8, right? Yeah, so in this problem, so a constant volume hydrogen thermometer is used, okay, to measure the temperature of a furnace. The pressure in the bulb at 0 degree centigrade is equal to the atmosphere. Okay. If the temperature of the furnace is 273 degrees centigrade, then what is the pressure in the bulb at furnace temperatures? So the furnace temperature is 273 centigrade. So first of all, the pressure P equals to 1 atm. So basically atmospheric pressure 1 atm at temperature T. Okay, at temperature yeah 0 degree centigrade. So that means 273 Kelvin. And if the temperature of the furnace T, so this is T1 and this is P1, T2 is 273 degrees centigrade. So that means 273 plus 273 Kelvin, 546 Kelvin, right? Then what is the pressure P2, right? What is the furnace? Yeah, so what is the pressure in the bulb at this furnace temperature T2, 546 Kelvin? So we calculate P2. So now in the problem, is very high temperature, right? So T2 is 546 Kelvin. Okay, it's a very high temperature. So because 273 degrees centigrade. Okay, so at very high temperature, okay, at constant volume, the hydrogen thermometer is basically an ideal gas. Okay, so you know that hydrogen gas is a real gas, but at very high temperature and pressure is low. Okay, 1 atmosphere, let's. So very low pressure and high temperatures, a real gas behaves like an ideal gas. Okay, so then you have to use ideal gas equations. So ideal gas equation at constant volume. Okay, so the constant volume. Okay, so what is the ideal gas equations? PV equals to RT, right? So if the volume R is a universal gas constant. Okay, so at constant volume, so at constant volume, okay, P is proportional to T, right? Right. So basically, so at constant volume, and high temperature low pressure. So T over Ti is a limiting case of limit of Pi tends to 0, P over Pi. Okay, so you can, so this is very correct way to write down, and this is basically is T1 over T2 is equals to P1 over P2. Okay, at very high temperature low pressure your P is proportional to T. Okay, behaves like an ideal gas. Okay, and at constant volume this. So therefore P2 is equals to P1 times T2 over T1, right? And P1 is 1 atm times T2 is 270. So T2 value is 273 degrees centigrade, that means 546 Kelvin, and T1 is at 0 Kelvin. So 546 and 0 degrees centigrade, that means 273 Kelvin. Okay, and this Kelvin cancel, so this gives you a 2 atm, right? So the pressure is 2 atm. Okay, okay, so let's check the answer. So 2 atm, but okay, so in the answer if you look into the options, okay, so option is given centimeter of mercury. So now you tell me that the 2 centimeter 2 atm equals to how many centimeter of mercury? Okay, how much centimeter of mercury? So 1 atm equals to 76 centimeter of mercury, and 2 atm equals to 2 times 76 centimeter of mercury, right? So 2 times 76 means 154, right? 152, right? Yeah, so 152. So the option C is correct. Okay. So 152 centimeter of mercury. It's clear? Okay, so far any question? Okay, so if there is no more questions, then I will move to the next one, right? So in the next question, okay, so in the interval, so this is the problem number 9. So in the interval 0 degree centigrade to 660 degree centigrade, okay, a platinum resistance thermometer is used for interpolating temperature on international scale, right? If the variation of resistance with temperature is given by RT this, find the values of alpha and beta. Given R0 this, R100 this, okay, and R446 44.6, okay, this, okay. So this is basically a different temperatures, okay, RT. So what is the given in the problem? Okay, first note down the given in the problem. Okay, so R, okay, so problem number 8, sorry 9. So at temperature T equals to 0, R0 is given, right? It's 10 ohm, right? And at the temperature, just a minute. Yes, so at temperature 100 at 44.6. So three different temperature is given, right? So at temperature T equals to at temperature T equals to 100, let's say degree centigrade, R 100 is also given, is 13.946, okay, ohm, and at temperature 444.6 degree centigrade, your R 444.6 is equals to 24.817 ohm. So this is basically given in the problem. This is given, right? And they follow the equations. RT at any temperature, the resistance is basically R naught 1 plus alpha T plus beta T square, right? So R naught. So how many constants are there? R naught, alpha, beta. Three constants are there, right? So in order to calculate RT, okay, for any temperature T, okay, so you have to know the values of R naught, alpha and beta, right? So R naught value also already given, right? 10 ohm, but the alpha beta value we do not know. Okay, so that's why there is also two values are given, R100 and R446. Okay, so these two values, okay, are used to calculate alpha and beta, right? Since we have to calculate two unknown quantity alpha and beta, okay, so let's say R naught is given, so we need two values of RT, okay, that is basically the initial values, right, at the boundary values. Okay? So R naught is the initial values and we need two boundary values, okay, to calculate alpha and beta. How we can how to do that? It's very simple. So first use, let's say T equals to 100. Okay, so if we wrote this equation T equals to 100, so it's R100 equals to R naught 1 plus alpha times 100 plus beta times 100 square, right? Now we know what is the values of R100 is already given, right, at 100 degree centigrade. So 13.946, so 13.946, and R naught is already given 10 is 1 plus 100 alpha and 10 to the power 4 beta. Okay. So this is basically 10 to the power square alpha. Now I can also do the same thing at T equals to 444.6 degree centigrade. Okay. So this is basically R44. So let's mark this equations in 1. Okay. And the second one is R444.6, which is equals to R naught 1 plus alpha 444.6 plus beta times 444.6 square, right? Okay, and this value, so R444.6 value also given in the problem. Okay, So it's 24.817. So 24.817 equals to R naught 10 times 1 plus alpha times 44.6 plus beta times 444.6 square. So this is basically your equation number 2 and this is 1. Okay, so there is a 2 equations, 2 unknown. Okay, right, alpha and beta. So the unknowns are basically alpha and beta. Okay, so solve these equations. How to solve these equations is very simple. So your equation is basically 1 plus the equation number 1 plus 100 alpha 234 alpha square equals to 1.3946, and the second one 1 plus 444.6 alpha 444.6 times 444.6 alpha, sorry, beta equals to 2.4817, right? Okay, so once you solve this, the alpha values of the alpha is 4.11 times 10 to the power minus 3, okay, per degree centigrade. Okay, because this is the degree centigrade and this alpha must be per degree centigrade because this is a dimensionless. Okay, so this is the per degree centigrade or the degree centigrade inverse. Okay, this is very bad way to write it. Per degree centigrade is the better way to write it. So per degree centigrade and beta minus 1.65 times 10 to the power minus 6 per degree centigrade square. Okay, so per degree centigrade square. Okay, so once you know the alpha and beta value, okay, we can calculate. Sorry, in the problem, I think, yeah, so problem is basically calculate the alpha and beta, so the values of alpha and beta. Okay, so we already calculated. Okay, so let's check the answers. Okay, so alpha value we got 4.11 times 10 to the power minus 3 and beta 1.65. So let's check the answer. Yeah, the option A. Right, so option A is correct. Okay, so any question? So this is basically your coupled equations. Okay, and you can easily solve. You just multiply it with okay, so once you subtract this, we can get another equations. Okay, because this one is cancels and you just multiply it with these equations. It's very simple. I mean, once you subtract this, we can get a one equations, another third equations. So you can get third equations is basically 2 minus 1, and in this equation there is only alpha and beta. So some coefficient times alpha and some coefficient times beta equals to some number, right? So then we can write alpha, okay, in terms of beta plus some number, okay, and plug these values into equation number 1. So plug this alpha value in equation number 1. Okay, we can get the values of beta. Okay. So once you know the beta, we can use these equations. Okay, we can calculate the alpha. Okay, so this is the way we can solve the couple equations. Okay, it's like a linear equation, so it's very simple. Okay, so in the next problem, so if not, then I'll move to the next question. So the last one, then I'll solve some other problems. So in the last problem, the resistance of a platinum resistance thermometer at 0 degree centigrade, 100 degree centigrade and 200 degree centigrade is found to be 3.5, 5.5, 7.44. Calculate the values of delta for platinum. Yeah, that's a good question. So what is delta? So you recall your class notes. Okay, so right. So what is delta? So delta is basically calendar correction factor, right? So your problem number 10. So in the problem number 10, first note down the quantities that is given in the problem. So at 0 degree centigrade, the resistance 3.5 ohm and 100 degree centigrade 5.5 ohm, 200 degree centigrade 7.44 ohm. Calculate the delta for the platinum. Okay, how do we compute? So this 0 degree is basically your ice point, right? And this 100 degree, so this is basically your ice point. Okay, this 100 degree centigrade, you are basically your steam point, and this is basically your bath. Okay, hot bath, right? So therefore the hot bath temperature theta is basically r theta minus r naught divided by r100 minus r naught times 100 degree centigrade, right? So I have to use this value, that is 7.44 ohm. Okay, and I calculate theta. Okay, using this formula, let's say theta p. I know this is a 200 degree centigrade, but once you calculate this theta p, then we calculate the error. Okay, or basically the calibration factor, right? So if you use this calculator, so theta p, then r theta is 7.44 minus your r naught is 3.5, r100 is 5.5 minus 3.5 times 100 degree centigrade, right? So the r theta is 7.44, but I do not know the bath temperature. Let's say 200 degree centigrade, I do not know. Okay, so I have to calculate using the calibrations. Okay, using the thermometers. Okay, the platinum resistance thermometer. Okay? Formula. So this is your formula to compute theta p. Okay, so this becomes yeah, so this becomes 7 point so this is, you just calculate this. Okay, so this is, gives you 197 degree centigrade. Okay, okay, so 197 degree centigrade, but here is given is 200 degree centigrade. Okay? So this is your true temperature. So 200 degrees centigrade, this is your true temperature. This is true temperature of the bath. Okay, but you calculate the bath temperatures. Okay, so this is your bath temperature. This is the calculated value is 197 degrees centigrade, and the true temperature is 200 degrees centigrade. But the true temperature, so this is the calculated value, but the true temperature of the bath that is given is 200 degrees centigrade, right? So I have to calculate the calendar correction factors. Okay, so calendar, sorry, yeah, so I have to calculate calendar correction factor. So this is a delta. Okay, so what is the formula for delta? Is theta is the true temperature minus theta p calculated value over theta over 100 square minus theta over 100. Okay, where theta, so this is basically your theta. So the true temperature of the bath theta is 200 degrees centigrade, and theta p is 197 degrees centigrade. So plug these values. So 200 minus 197 over, so 200 over 100 square minus 200 over 100. Okay, so this is basically 3 over 4 minus 4 minus 2, so 3 over 2, right? So which is basically 1.5, right? Let's check one more time. 3 and 4 minus 2 is 2. This is 2. So this gives you 2. This gives you 2. So 2 square. So this gives you 2 square, and this is 2. 4 minus 2. Yeah. So 1.5. Okay. So let's check the option. Yes. So the option B is correct. Okay? So 1.5. Calculate the values of delta for platinum. So this delta is nothing but the calendar correction factors. Okay. 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 So far any question? Okay, so if not, then I will discuss okay, so let's discuss something on the basically the the real gas. Okay, okay, so for van der Waals gas, so let's start with the van der Waals gas. Okay, so for van der Waals equations, okay. The van der Waals equations is basically equations of state is P equals to RT over V minus B, okay, minus A over V square. So this is for 1 mole, okay, or n equals to 1, and you calculate the PC, VC, TC. So the VC is 3B, okay, and PC is basically your, yeah, so PC, so basically also know that the TC is 8A over 27 RB, okay. So you can use this formula to calculate PC, right? So PC is basically RTC over VC minus B minus A over VC square. So if we use these values, okay, TC and PC are, so this basically 8 AR times 27 BR times 3B minus B, okay, minus A over 9B square. So this gives you A over 27 B square. Okay, so this is the critical pressure PC. And to also know PC, okay, TC and VC, you can calculate the critical coefficient. So what is the critical coefficient? So critical coefficient eta, okay, so this is basically RTC over PCPC, so which is equals to 1 for any ideal gas, but once you calculate for van der Waals gas, okay, so it becomes your R and TC is 8A over 27 RB, right, and PC your A over 27B square times 3B, so this is basically 8 over 3, right. So this is 8 over 3 and this is eta C, okay, and 1 over eta C is 0.375, okay. So sometimes 1 over eta C are important than the eta C, but the critical coefficients are eta C. So this is basically 8 over 3 for van der Waals gas, okay. So now if we consider a deuteracy gas, okay, if you calculate this value, the critical coefficient value for the deuteracy gas, okay. So for deuteracy gas, for, yeah, so for deuteracy gas, yeah, so for the deuteracy gas, the equations of state is P over P equals to RT over V minus B exponential minus A over RTV, right? So again for n equals to 1, okay, so 1 mole, okay. So for n equals to 1, so you're going to calculate TC, PC, VC. So for this case, so this VC actually 2B and TC is A over 4RB, right, and PC is A over 4 square B square, right. So we calculate the critical coefficient. So critical coefficient, that is eta C, okay, so RTC over PCVC, so this is basically E square over 2, right. and 1 over eta c. So this is the okay, so this is square over 2, and yeah, 1 over eta c is 0.271. Okay. So for van der Waals gas, this is 0.375. Now if you know this value 1 over eta c value for different real gas, okay, so it's basically neon, okay, argon, okay, and chromium and xenon, okay, and the 1 over eta c value, okay, basically 0.287, 0.292, 0.291, 0.290, right? So these are very close to 0.271, right? And this is very high value, okay. So the DTDC gas is very, I mean, the equation substrate is very close to describe this, the behavior of neon, argon, chromium and xenon, right? Because the 1 over eta c value is very close to this gas. Okay, these equation substrates, okay, DTDC, not the van der Waals, because van der Waals is 0.375, okay, slightly higher value. So that is the one of the way we can identify the what is the correct equations of states, okay, for a gas, okay, for a real gas, okay. So this is very close to this value, okay, it's not exact. So yeah, so that is the points I want to discuss. Okay, so you have any questions, you can ask, okay, otherwise I'll stop the meeting here. Okay. Okay, so it seems there is no more questions. So okay, so then I will stop the sessions here, okay, and yeah, see you on the next Sunday at 4 p.m. Okay, thank you, bye bye.